Hello everyone. Till now we've been seeing symmetric key ciphers, right? So we saw that a single key is used for decryption and encryption, and to share message between two people, those two people has to exchange the keys in some secure way. So if I want to send a message to someone, I can encrypt it using a encryption key. Example, for in DES we can encrypt it using the key, but I have to transfer that key to that person somehow. If I can reach him physically, I can write the 56-bit key on a piece of paper and give it to him, right? So that's no problem. But what happens is, what if we want to communicate with someone who is very far away? We cannot reach him personally, or we cannot send the key. That is where something called asymmetric encryption, asymmetric key cipher encryption comes in. Asymmetric key ciphers. What are these? Asymmetric encryption is something like you use key 1 to encrypt, and whatever key 1 encrypts, only key 2 can decrypt. Alright, so these two keys come in pairs. Always asymmetric keys come in pairs, and whatever one key locks, the other key unlocks. So what you can do is you can encrypt using this key and send the message, and now only the person with this key 2 can decrypt. So what you do is you make the encryption key public and you keep the decryption key private. Let's say I have a pair of keys, key 1 and key 2, and what I do is I say everyone, whoever wants to send me a secure message, use this key to encrypt. And now anyone who wants to send me a message will encrypt it using this key, because anyone can obtain this key because this is public, and only I can decrypt it because this is private. Similarly, if I want to send a message to someone, I will use their public key. Remember that once we encrypt, even the public key cannot decrypt the message without the private key. All right, so this is how asymmetric encryption works. Also, one of the properties of asymmetric encryption is it is based on mathematic functions, right? It is based on mathematic properties or mathematic operations like finding prime numbers, everything. So whatever you encrypt using asymmetric key encryption, the encryption thing should be numbers. So if you want to send a message hello to someone, this hello cannot be encrypted. It should be converted to numbers because asymmetric key only works on numbers. So you will have some algorithm which will convert hello to numbers. We can use a basic ASCII table, and you can just find the ASCII values, and find the numbers, right? So that's not a big deal, but you should use numbers before encrypting them. All right. So yeah, that's it for asymmetric key encryption. Now we'll look at something called RSA encryption. RSA stands for reversed Shamir and Edelman. Reversed Shamir and Edelman. So these are the three people who discovered RSA. Yeah, it was named after them. RSA is one of the most widely used encryption standards even today. So it's really uncrackable because it is based on prime factorization, which is really hard for computers to do. What I mean by that is you can multiply any two numbers very easily. Very easily. I mean, let's say you can multiply 5 into 3 is equal to 15. That's easy. But getting this 5 and 3 from 15 is really hard. This might not sound obvious because the numbers are very small, but once the numbers get big, once the numbers are in range of hundreds of digits, then Multiplying two numbers is really easy, and getting back what numbers multiplied to get this number is really hard. So RSA is based on that. So RSA follows some specific steps. We'll go on to see what those steps are. First of all, let's assume Alice wants to send a message to Bob B. All right. Now what Alice does is she selects two prime numbers P, Q, and calculates P into Q is equal to N. All right. Simple enough. These two prime numbers better be some big prime numbers, so that getting the reverse is really hard. Again, remember that even if P and Q are like 150 digits, we can multiply them easily, and the result will be of 300-400 digits. And getting back these two digits from by computers is even hard for supercomputers. All right. So we take two big prime numbers and we multiply them to get N. All right. Now what we do is we select we use a function called phi of n, which means p minus 1 into q minus 1 is equal to phi of n. So this function, what it does is you calculate another number phi of n, which is p minus 1 into q minus 1. Remember, this works only when p and q are prime. All right. Now what you do is you select E such that E is less than phi of n and E is a co-prime of phi of n. What is co-prime? Co-prime means it does not share any prime factors with phi of n. All right. Now remember, A wants to send a message to B, and B is doing all these things so that A can send a message. What B is doing is B is basically creating a lock, only which he can open, and he will give the lock to A, and A will put the message inside, lock the box, and then give it to B in an unsecure way, so that anyone who obtains the lock cannot open it except B. So we are creating a lock. B is creating a lock, and we'll give the lock to A. So what we did was we selected P and Q and calculated N. P and Q are prime numbers, and we selected phi of n such that P minus 1 into Q minus 1, and this works for prime numbers, and we have this number. Now we selected E such that E is less than phi of n and E is a co-prime of phi of n. That's also fine. Now what we do is we calculate D such that D is a multiplicative inverse of D is a multiplicative inverse of E mod phi of n. Alright. E is a multiplicative inverse of E mod phi of n. Multiplicative inverse means once you multiply two numbers, they should get you 1. Alright. Now for the fifth step, what you do is you advertise N and E as your public key. This is the lock you created, which can be opened by D, and only you know D because you calculated it, and you calculated it, and only you know D. You send N and E to Alice or anyone on the internet, and you say whatever you want to say to me, use these numbers to encrypt and send the message to me. I'll decrypt it. So what Alice will do is, let's say Alice's message is K. Alice will do K power E mod N, which will be equal to, let's say, A. Okay. Now how you decrypt it is you say A power D mod N, which will get you K back. Here remember, K is the message we want to send and A is the ciphertext. All right, this is how RSA algorithm works. This is a very elegant way of encrypting things. It is very prevalent in even even by today's standards. And what people do is people create RSA key pairs and they put it on the internet publicly. So publicly it is put on something called as key servers. One of the examples of key servers is MIT key server. Massachusetts Institute of Technology, they have a key server. So you can just Google them and yeah, you can find the MIT's key server. And now if you want to send a message to someone, let's say you have to send some message to Krishna. And you probably can, if you know the email, you can find the his public key, and you can use that public key to encrypt your message and send it to him. And what happens is this message cannot be read by anyone except Krishna because only he has the public key. This key server is very slow. We'll try something else. Yeah. See, I just googled a random name. Let's say you want to send a message to this Krishna. Yeah, or this person is fine, right? Let's say you wanted to send it to him. You can click on this and you can find the public key of him and you can encrypt the message and you can send it to anyone. Yeah, this key server is very slow. We'll try something. Yeah, it worked. This Christian Bernard has 4 or 5 keys, and maybe we'll use this. Yeah, this is his public key. You can use this public key to send him anything. All right. So yeah, that's it for RSA. We'll quickly recap the whole algorithm once so that we get familiar with it. We were looking at public key encryption. We were looking at asymmetric key ciphers. So exchanging this pre-shared key, symmetric keys is really hard, especially over the internet where we cannot guarantee anything. So what we do is we create something called asymmetric keys. So whatever is locked by the public key can only be decrypted using the private key. And this is done by mathematical functions. So plain text or any objects cannot be encrypted. You have to find a way to convert anything to a number and then the number can be encrypted. One of the implementation of this is RSA. This is invented by 3 people, Drivers, Shamir and Edelman. And the algorithm goes as follows. You select 2 prime numbers P and Q and you find n by multiplying them. Then you find phi of n such that P minus 1 into Q minus 1 is equal to phi of n. Alright, so that's also easy. Now what you do is you select a number E which is a co-prime of phi of n. And you calculate D such that D is a multiplicative inverse of E mod phi of n. And then you advertise n and E as your public keys. And whatever message is encrypted using this can be decrypted only by using this D and N. So this is the public key, this is the private key. You keep this key as private and you publicize this and say, this is my public key. Whoever wants to send me a message, send me the message by encrypting it with this. And how you encrypt the messages, if K is the message, you say K power E mod N and you get an answer A. You can send this over to anyone and no one will be able to decrypt it. How you will decrypt it is you raise A to the power of D, your decryption key, and you say mod N, which will give you back K. Now you might ask, if I am able to calculate D, why can't anyone who's getting this message can calculate D, you know? We were able to calculate D because we know phi of n. And we know phi of n because we know P and Q. So that's the whole beauty of RSA encryption. No one will know P and Q, right? So even if they know N, calculating P and Q from N is very hard for even supercomputers. It takes thousands of years. So that's the whole basis on which this RSA encryption works. Alright, yeah, that's it for RSA encryption and asymmetric encryption. Yeah, this solves our first problem of anonymity, confidentiality, right? When we are looking at what are the elements of security, we saw that we need confidentiality, then we need integrity, and then we need availability. Yeah, these three things we needed. Now we have nearly solved confidentiality, right? If I want to send a message to someone, I can send it with confidence that if I encrypt it using public private keys, I can get the message across without no one else seeing. So we have solved confidentiality. In the next video, in the next set of videos, in the next series of videos, we'll see how to solve integrity. All right, that's it for this video. I'll see you in the next one. Thank you.